Hello everyone, Dr. Data Science here to teach you data science methods and tools today, tomorrow, and beyond. The purpose of this video is to prepare you for your next machine learning exam. This video covers several important topics, including linear regression, logistic regression, and regularization, which is important to avoid overfitting, as we will discuss very soon. This video also contains several practice tests, and I will show you how to solve them step by step. If you like this video, don't forget to join the Dr. Data Science team. Let's get started. For learning any machine learning method, there are four key components that you need to keep in mind. The first one is the data that we can learn from. And the second one is a model of how to transform the data. I'll explain these two components using linear regression. So in a linear regression problem, we have a set of inputs and outputs. Outputs are typically scalars, meaning that they are single numbers. For example, when you want to predict house values, in this case, each house is associated with a number. On the other hand, for inputs, we typically have several features or predictors. For example, we may have a square footage of houses, safety scores, public education scores, and so on. Therefore, inputs are arrays of numbers, or mathematically speaking, vectors. In terms of notation, I use the superscript I to denote the data point or example number. So xi means that this is the ith data point that we have in our data set. And then I use the subscript 1 to d to index features. So if you look at this data set that we have represented here, we have n data points, meaning that n input-output pairs, and each input has d features or predictors. Next, we need to talk about how we can transform this data, which means here that if we take these inputs xi, how we can predict the corresponding output. Linear regression is based on this very simple model that we can find a weighted sum, also known as a linear combination of input features, to find the corresponding output. So in terms of notation, here I use H because this stands for hypothesis. Xi is the input, and then we put it into this or plug it into this equation that we have here, which is the equation of the line. And this will give us the output that we are looking for, which is a single number or a scalar. Something to keep in mind is that these parameters, theta 0, theta 1 to theta d, are unknown. And therefore, the main purpose of here using machine learning is to be able to estimate them or find these parameters. And remember that theta 0 is known as the intercept or bias term. The other two components that we have is one, an objective function that quantifies how well the model is doing. In other words, we made some assumptions in the previous slide, and now we have to look at how good or bad this assumption is given the data that we have. And then the fourth component or the fourth step is we need to find an algorithm to adjust the model parameters, meaning theta 0, theta 1 to theta d. Again, in terms of linear regression, the objective function, which is a function of the unknown parameters theta 0, theta 1 to theta d, is mainly something known as mean squared error. So if you look at it, we have 1 over n, summation from 1 to n. So that means that we want to find average of something. But what is that something? that's what we have here, which means that we have these predicted values. So this is what the hypothesis or the model is giving us. And these are the actual outputs. And we subtract them from each other and raise this to the power of 2. So I can also show you where these theta 0 to theta d, these parameters are by just putting the equation for the hypothesis that we have here. So if you remember from the previous slide, our hypothesis is that we have this weighted sum or linear combination of features. And we want to minimize the amount of error that we have, right? So we want to minimize this mean squared error. Obviously, there are other ways that we can measure error here, for example, using absolute value instead of using a squared error. However, this makes it really simple to solve the problem in the next step. So that's the main reason that mean squared error or MSE is very popular for regression problems. And the last step is typically very straightforward because now we have this objective function, and now we want to find for what values of these parameters we minimize this cost function or objective function. Something that I want to add here is about this argument notation, because you may not be familiar with this. So if you look at here, let's say that we have a function that looks like this quadratic function that we have. And I call this j of theta, and this is just a univariate function, meaning that has only like a single variable. And you can see that for theta equals 1, this function reaches its minimum value, which is 4. So you are probably familiar with the minimum notation. So when we say we want to find minimum of j of theta over all values of theta, we just look at the minimum value of this function, and that's 4. But when we say argument, means that for what value of theta or what value of input, this function reaches its minimum value, and the solution is 1, right? So for theta equals 1, this function reaches its minimum value. And that's what we really need here, right? Because what the minimum value of this cost function or objective function j is really doesn't matter as much for machine learning purposes. But what really matters is that what those combinations of input parameters or unknown parameters theta 0 to theta d are. So these are 4 key components that you need to keep in mind for linear regression, for logistic regression, or any other machine learning method. So having this said, now let's look at the first practice test that we have. Let's say we have a data set in which each data point has only one feature. So what this means is that x1 to xn are also scalars, and we are not working with vectors. And the reason for this is that this problem, we want to solve this optimization problem by hand. So therefore, it's much easier to work with the scalars. But there are important things that we want to focus here that is the reason that we have in this problem. So this is something that is known as the ridge regression problem, and I will tell you very shortly why we call this ridge regression problem. But anyways, the cost function here, or the objective function that we have, is very much similar to what we saw earlier, which you have this summation of actual values minus predicted values. And here I have a note that why predicted values here has only one term, because what we have done is that we have set the bias term to 0, right? So remember that xi here is a scalar. So if you use our hypothesis that we had earlier, this means that our hypothesis is theta 0 plus theta 1 xi, right? So we don't have extra terms because there's only one feature here. And then in the problem, we basically assume that theta 0 should be 0, and this gives us this very simplified form. So if you remember from calculus, this is actually the equation of a line that goes through the origin, right? And theta 1 is the slope of this line. So now let's go back to our optimization problem. So this first part is measuring the difference between actual and predicted values. But we have this second term, which is some fixed constant like lambda times theta 1 raised to the power of 2. So this is a part that we didn't have in the previous slide. But for now, it doesn't really matter because we want to solve this ourselves. So what this question asks is to find the optimal solution, meaning that for what value of theta 1, this objective function reaches its minimum value. And it asks us to find this solution in terms of these two quantities, s of xx and s of xy, were defined here. So s of xx is basically the summation over I of xi squared. And s of xy is the summation from 1 to n of xi and yi's. And the second part of this question asks what will happen if lambda goes to infinity, meaning that if lambda is a large number. So obviously looking at this optimization problem, if we set lambda equals to 0, we totally get rid of this point. And that's very much similar to the mean squared error that we just had. But we want to see what will happen when we add this extra term. So here the path that we take is as follows. We have a problem where we want to minimize a function. The function only has one variable, which is theta 1. And based on what we learned from calculus, we can use first derivative test, meaning that find the derivative of this objective function and set it equal to 0. So let's do this step by step. So I give a name to this objective function that we have. I like to call it j, and it has only one variable. Next, I need to find the derivative of that with respect to the only variable that we have, which is theta 1. And because we can take the derivative inside the summation, so now we have the summation from 1 to n of derivative of this term, right, the square term that we have, plus lambda times the derivative of the second term with respect to theta 1. The second term is easy to find because when we have x squared, we know that the derivative with respect to x is 2 times x. And that's the same thing here. It's just a different name. We have theta 1 squared. What is the derivative of this with respect to theta 1? Is 2 times the variable, which is theta 1. However, we need to find the derivative of this square term here too. And if you're feel comfortable with chain rule, you can probably do this very quickly. But I will explain here how we can solve this in more detail. So the first thing is that we can give a name to whatever we have inside these parentheses. I like to call this z. And z is defined as yi minus theta 1 xi. So now what we want to do is to take the derivative of z raised to 2 with respect to theta 1. And we know that we can use chain rule and first find the derivative with respect to z. And after that, find the derivative of z with respect to the original variable, which was theta 1. Again, the first part is easy because the derivative of z squared with respect to z is 2 times z. And remember, z is defined here. On the other hand, we have to find the derivative of z with respect to theta 1. And if you look at here, yi is given, is a fixed number, right? That's part of our data set. So derivative of constant is 0 because it doesn't change. And then when we want to find the derivative of the second term with respect to theta 1, so theta 1 is the variable, and everything else is fixed or constant, which is -1 times xi. And we know that the derivative of, for example, 2 times x with respect to x is 2. It's always that constant that is multiplied by a variable. And with the same logic here, we can say that this derivative would be -xi. So the constant that is multiplied by theta 1. And we can simplify this. So we have -1 times 2, which gives us -2, yi minus theta 1 xi. And remember, we have also this extra xi that we have here. So this means that now we have found the derivative of the objective function with respect to theta 1. Let's put this together. So if we just put everything together here, we get that the derivative is -2 times the summation from 1 to n of yi minus theta 1 xi times xi. So that's the one that we found using the chain rule, plus 2 lambda theta 1. And now we have to set this derivative to 0 to find the minimum value of this function. So here I have set this derivative equal to 0. And the first thing I noticed that there's this factor 2 and 2 here. So I'm going to divide both sides of this equation by 2 so that I can get rid of these 2 extra parameters that I have here. And this gives me the negative summation from 1 to n of yixi. So that's like also something that I have done here. I've done this multiplication, yi by xi, and then theta 1 xi by xi. So that's what we have here. And this gives us the summation of yixi's plus, because remember, there's a negative sign here. So negative sign by negative sign, we get plus theta 1, and then summation of xi squared. So I can take theta 1 outside of the summation because it doesn't have any dependence on I, right? But anything that depends on I should stay inside the summation. Plus, I have this lambda theta 1 that I put here. If we remember from the problem statement, we call this term s of x and y, and then we call this s of x and x. And therefore, now we can factor this theta 1 between these two terms, and this s of x and y goes to the other side and becomes positive. And now we can divide both sides by this constant, and this gives us the optimal solution that we are looking for. So as you can see, even though we modified the objective function for linear regression, still we are able to solve this problem. And the key thing here is that we use one-dimensional or scalar features or predictors. That helps a lot to simplify the problem. So what would happen if lambda goes to infinity, meaning that lambda is a very large number? Let's say lambda is 1 million or 1 billion, right? What will happen is that because it's in the denominator, this means that this theta, the optimal solution that we are looking for, will go to 0, right? Because we are multiplying this fixed number by a very large number. So what this means is that in this problem that we had, if lambda equals to 0, we are just fitting this model to the data, and we are not putting any control on this optimal solution. And if lambda goes to infinity, meaning that it's a very large number, we are not really solving any problem, because what we are doing is that the optimal solution will be very, very close to 0. And in some ways, we can say that this optimal solution ignores the data that we have and its underlying structure. And that's the idea of regularization. Regularization is achieved by containing the model parameters. And this typically means keeping them as small as possible by adding an additional term in the objective function. So if you remember, when we had the problem statement, so that was the additional term that we added, which was some fixed number lambda times the optimization variable to the power of 2, which you can say that this measures the magnitude or the norm of this variable. If lambda equals to 0, we completely get rid of this term. And here I have an example where we have these data points, right? So X, Y pairs, and we want to find a line that goes through this sort of like data set that we have, right? And if you look at here, we have this highlighted area. And let's say for some reason, we believe that these two data points are outliers or not really representative of the problem that we want to solve. So in this case, if we set lambda equal to 0 or get rid of this regularization term, we don't have any control on the slope of this line, right? And these 2 points are definitely able to pull this line towards the upside, right? But what would happen if we use regularization here, as you can see on the right side? Now we can control the slope of this line. And as you can see, compared with the one that we have on the left side, the slope is decreased, right? So you can see here, this line now is closer to this point that we have here. So that's the main idea behind regularization that allows us to contain the model parameters. And the main reason to do this is when we think that we have a problem known as overfitting. In the next slide, we are going to see what it means to have underfitting and overfitting. To understand this topic, let's consider a synthetic data set, meaning that we define a true function or ground truth function, and then we sample a few points or samples from this function, and we add a little bit of noise to it, right? So this is sort of like the data set that we have. And here we use something known as polynomial regression, meaning that we can use polynomial features and then apply linear regression to solve the problem, which will allow us to find nonlinear relationships in the data. On the very left side, we have a degree 1 polynomial, which means that it's just linear regression or a linear function that we are trying to find, this blue line that we have. And then we increase the degree here to degree 4 in the middle figure that we have. And then on the very right side, we use a very high degree polynomial function. So when we set degree equals 15. So just by visually looking at these 3 figures, we see that degree 1 is too simple for this problem that we have because it's not able to capture nonlinear relationships. And that's what we call as underfitting. If you look at on the right side, where we use degree 15, you can obviously see that this predicted model that we have, this sort of like blue curve, is too sensitive to the noise that we have in the data, right? So it does a very good job of capturing the training data points, but obviously this doesn't represent the true function or the ground truth function that we have. And that's what we call as overfitting, meaning that the model is too complex for the data that we have. And when we have overfitting, it means that the model that we learn performs well on the training data. But remember, machine learning is always about generalization error, meaning that how it will perform on some new testing data points. And obviously, if I have in this region some test points, for example, here or here, you can see that the actual and the predicted values are really, really far from each other, probably even worse than the linear regression that we have on the very left side. So that's the idea behind overfitting. Another way to look at this is through bias and variance. We can define bias as the error between average model prediction and the ground truth. It describes how well the model matches the training data set. A model with a higher bias wouldn't match the data set closely, and a low bias model will closely match the training data set. Therefore, if you look at the figure that we have on the left side, we can see that this model has high bias. But if you look at the one on the right side, which represents overfitting, this model has low bias because it closely matches the training data set. But what is variance? Variance refers to the changes or variations in the model when using different portions of the training data set. To put it in simple terms, variance is the variability in the model prediction. It means that how much the machine learning function can adjust depending on the given data set. If you look at the degree 1 that is on the left side, we can see that this model has low variance. It's not really sensitive to the changes in the input data. But the one that we have on the right side for overfitting, it shows you this model is very much sensitive to the changes in the input data and is able to change very abruptly. So this means that it has high variance. So this is another way to look at underfitting and overfitting based on bias and variance. Now let's take a look at another practice test. In this case, we have again a linear regression problem where is defined in this form. So this is very much similar to the problem that we had before, except the fact that now input features are not the scalars and they are vectors. That's why we use this norm of vectors to define the objective function. But just to show you how we can solve this problem, remember this lambda, which shows the strength of the regularization. When we increase that, the solution gets closer and closer to 0, meaning that the machine learning model that you learn is less sensitive to the input data. And what this means is that the bias will increase, right? On the other hand, the variance will decrease because the model then is not very much sensitive and the solution becomes closer and closer to 0 as we increase the regularization parameter lambda. So you see that just by looking at the previous slide where we had those simple examples, we can solve this somewhat complex problem, which is using norms for vectors. But at the end of the day, it's just a simple idea about regularization and its impact on bias and variance. This practice test looks at overfitting and underfitting in a little bit different way. So on the x-axis here, we have something known as model complexity. For example, let's say model complexity is the degree of polynomial that you use for regression. And then you have error on the y-axis. And here we obviously see training error and testing error. Obviously, if training error and testing error are comparable, that means that the model does not overfit or underfit. And when they diverge from each other, that's where we have to be very cautious. So here it says that for what values of P, where P is the model complexity here, we have overfitting, right? So remember, overfitting means that the model performs well on the training data, but not on the testing data, right? And you can see that that's where this happens, right? So model B at both 20 and 30, this is where we have overfitting. But before then, for example, like here, we only have underfitting, right? Because you can see that the training error is high and the testing error is high. But on the other hand, on this side, you can see that the training error is low and the testing error is high. And one way to avoid overfitting in general is to use regularization. There are also other possible ways too. One way, for example, is to add more data points. But in many cases, you may not have access to additional data points. As you can see here, overfitting, underfitting, bias, and variance are very fundamental topics in machine learning, and they appear a lot in machine learning exams. So here it says that which of the following are reasons why you may adjust your model in ways that increase the bias, right? So remember, you increase the bias when you believe you have overfitting. That means that you have low training error and high validation or testing error. So that's one reason that you may want to increase the bias. The other reason is when you believe you have few data points, right? Because when you have few data points, you still have this problem that noise in the data has a larger effect on the model. And as I mentioned earlier, one method to reduce overfitting to the noise would be to increase the bias. But this doesn't have anything with linear separability of data, at least the way that we have this problem. And you can see that when the data is nonlinearly separable, we probably need a more complex classifier or decision boundary, right? And higher bias would reduce the complexity of the decision boundary. So that's something that will have some sort of like opposite effect that we don't really look for here. So here the idea is that we believe we have overfitting and we want to increase the bias. After discussing linear regression, regularization, overfitting, and underfitting, let's very briefly review logistic regression, which builds upon linear regression. Logistic regression is used to estimate the probability that a data point or an instance belongs to a particular class. In the simplest case, we assume that we only have two classes. For example, whether or not it will snow tomorrow. So therefore, we have two outcomes, which we call them C1 and C0. Similar to linear regression, we probably have multiple input features. Let's say we may have temperature, humidity, and some other information. And the goal of logistic regression is that given these inputs or features, we want to find these probabilities, right? We use conditional probabilities because we want to find probability of this data point falls into C1, given the features, and also probability that falls into C0. Logistic regression, as I mentioned earlier, builds on linear regression, except that now we are trying to predict probabilities instead of predicting something continuous. The first step of logistic regression is very much similar to linear regression, where we find this weighted sum or linear combination where these theta 0, theta 1 to theta d are unknown parameters or coefficients. However, we cannot use this linear combination as a probability value because we know that probabilities are always between 0 and 1. So how can we transform the data in that way? We can use something known as the logistic function or sigmoid function, which is given here. The logistic function at any point t is 1 over 1 plus e to the negative t, where e here is the famous constant in mathematics, where e to the 1 is 2.7 approximately. So what this means is that for any input that we give to this function, the output or the range of this function is always between 0 and 1, which is great meaning that we can interpret this number as a probability score. So to recap what we just talked about, logistic regression has a linear regression part or linear combination, and then we have the logistic function. And that's why we call it logistic regression. And even though in the name we say regression, this is for classification problems, meaning that when outputs are discrete. In this case, we only have two outputs, 0 or 1. And that's the main hypothesis or model that we have, that this is the probability that xi belongs to C1. And we have to find an objective function that describes how well this model fits the data that we have. But before getting there, what about the probability that xi falls into C0? Remember here we have two possible outcomes or classes. And based on the laws of probabilities, the sum of probabilities must equal 1. So this means that now we can automatically find probability that xi falls into C0, which is 1 minus probability that xi falls into C1. And we can show that here, that this probability has this form, which is e to the negative t over 1 plus e to the negative t. And this hypothesis is now complete because we have both probabilities that we wanted to find. What about the objective function? Remember, for classification problems, we cannot look at the class labels or targets as their numerical values, because we can just assign them any two distinct numbers we want. So we need to find a different way to find a meaningful objective function. First, remember, in machine learning, we mainly have these objective functions, which is the average of the error or cost or the mismatch between each actual value and predicted value. So here the cost has this form that when y equals 1, the cost is negative log of h. And remember, h is what our model, our hypothesis returns, which is here the output of that logistic function. And then when y equals 0, it's negative log of 1 minus h. In order to understand this, first you need to remember what a logarithm function is, or how it looks like. So that's what we have on the right side here. So when the input of the log is 1, the output is 0. And then when we have values between 0 and 1, the output is always a negative number, and it actually goes to negative infinity as we get closer and closer to 0. With this in mind, now let's look at that negative log of h, the first one, which is the blue curve here. So if h is equal to 1, negative log of 1 will give us 0. So we are at here. And then if h is very close to 0, log of h would be a negative large number, like negative infinity. And then we have this negative sign here, which gives us plus infinity. So that's how it is. And you can see what this means is that because this h is a probability, if we are 100% confident that that data point belongs to class 1, we have to pay 0 penalty. But as we get less confident, we have to pay a penalty that increasing exponentially, right? So you can see that this now will have a very high slope, and we want to be to avoid to be close to 0, meaning that we want to have probabilities that they're closer and closer to 1. And now if y equals 0, right? So now we want to have exactly the opposite side of this. The error we pay is 0 if the probability that that data point belongs to class 1 is 0, meaning that that data point belongs with 100% chance to class 0, right? So you can see that here, if I set h equals to 1, I get negative log of 1 minus 1, which is negative log of 0. Sorry, if I put h equals to 0, we get negative log of 1 minus 0, which is negative log of 1. right? And log of 1 is 0, so that's where we are. And then as h gets closer to 1, which is something that we don't want in this case because y equals 0, then we get negative log of 1 minus 1, which means the negative log of 0, and that's where we go to plus infinity. So that's how we can understand the cost function for logistic regression and other binary classification problems. So the key thing here is that do not use mean squared error when you have classification problems, because in that case, you're actually looking at the class labels with their numerical values, which is wrong. The other thing that you need to keep in mind here is that we can actually simplify the cost function that we had, and this is known as cross-entropy laws, which is very popular for other binary classifiers, including like convolutional neural networks and so on. And we can show that the cost function in the previous slide can be written as negative y log of h. H is the hypothesis, the output of the logistic function, minus 1 minus y log of 1 minus h. So let's verify that this is actually the same as what we had in the previous slide. If y equals 1, so here we get 1, here we get 1 minus 1, which is 0. So we get rid of this term. So that's what we have here. So we get negative log of h. And when y equals 0, right, when you plug in it here, you can see that we get 0 and then 1 minus 0, which is 1, right? So we get negative log of 1 minus h. Feel free to pause here and do this on your own, but you can see that this gives us exactly the same result as we had before. So for y equals 1, we get negative log of h, and that's exactly what we have here. So having that, now we can solve that optimization problem for logistic regression. But what I want to focus here is about evaluating the performance of classification problems, because obviously here working with discrete labels or targets, and we cannot just use mean squared error to see how far the predicted and actual values are. So here we need to have a different way of analyzing the performance of classifiers, including logistic regression. And the first thing you need to know is something known as confusion matrix. So as the name suggests, it's a matrix where each row corresponds to actual classes and each column corresponds to predicted classes. And remember, here it's a binary classifier, so we have only negative and positive, or 0 and 1, or true and false, right? And we basically find these four entries, right? So this one means that the actual class was negative and we predicted negative, so that's true negative. This one means that the actual class was positive and we predicted positive, so that's true positive. And obviously, these are the ones that we want, true negative and true positives, but the classifier may not be perfect and have some errors, and that's where we get false positive, meaning that it's predicted as positive, but it's actually negative, and false negative, which means that it's predicted as negative, but it's actually positive. Given this, we can define, for example, accuracy, which is the sum of the diagonal elements over all sort of like inputs that we have in our data sets, or all the data samples that we have. But we also have other interesting metrics, including precision and recall. So precision, we can look at it that we are looking at the problem in this form. So it's true positive over true positive plus false positive. And what it measures is what proportion of positive predictions was actually correct, right? So we want to see among samples that we label as positive, how many of them are actually positive. On the other hand, recall looks at the problem in this way, meaning that we have true positive over true positive plus false negative, meaning that what proportion of actual positives was identified correctly. right? So in this case, we look at all the samples that are actually true or positive, and we want to see how many of them are predicted or labeled as positive. So one is more sensitive to false positives and the other one to false negatives. Because now we have these two metrics, there is a way to actually combine them together, and that's known as F1 score. And that's basically the harmonic mean between precision and recall. So if you're familiar with harmonic mean, it's 1 over precision plus 1 over recall. You can do some math and you can see that this means that now we have 2 times precision times recall. And in the denominator, we have precision plus recall. And remember, all these values, precision, recall, F1 score, they are between 0 and 1. And higher values indicate better classifiers. So meaning that if you find precision, recall, and F1 score all equal to 1, this means their classifier is 100% accurate. So these are important ways to evaluate classification problems. There's also another one that is quite popular in machine learning exams known as receiver operating characteristic, or for short, we call it ROC curve. So what ROC curve does, as you can see here, plots true positive rate versus false positive rate for classifiers that we have a threshold, right? So remember, for example, for logistic regression, because it gives us a probability score, we don't have to set the probability always to be at 50% to decide whether a point belongs to class 0 or class 1. We can actually move that threshold, right? And the key thing is that as we move that threshold, how these true positive rates and false positive rates change. So you can see here we have like this classifier showing using this orange color that we sort of like have these true positive rates and false positive rates for each of these threshold, and this gives us this picture. So it shows us the trade-off between these two metrics. And obviously, we want the true positive rate to be as close as possible to 1 and false positive rate to be as close as possible to 0. This means that an ideal classifier should reach to this upper left corner and have a form like this, meaning that it has true positive rate very close to 1 and false positive rate very close to 0. It is also very common in this case to use something called area under curve, because as I said, the best case scenario is something like this, which means that the area of this square, which is 1 times 1, which is 1. And here you can see that, for example, this area under this curve is 0.79. So if you don't want to show the entire plot, you can just summarize it by looking at the area under the curve. And usually it's very common to draw this 45-degree line and say that this is a random classifier, or this corresponds to a random classifier. Meaning that if your classifier doesn't even look at the input features and just randomly classify input data points, that's where you get. And you obviously want to do better than this, meaning that you want to be upper side of this 45-degree line. But you don't really find very much explanation on this on different online resources and textbooks. So in the next slide, I'm going to show you how to actually understand this better. So what is a random classifier? Let's make some assumptions. Let's say you have a classifier that predicts true or positive, right? We use this interchangeably here with probability P, and predicts a false or negative number or class by 1 minus P, right? So this means that this classifier doesn't look at all at input features and randomly assigns a label to each input. And let's say also for simplicity, I assume that half of the data points that they have are positive samples, half of them are negative samples. This is not necessary, but definitely simplifies the problem. So now let's find these true positive, false positive, true negative, and false negative, which then allows me to find this true positive rate and false positive rate. So what are the true positives? means the sample that are labeled positive and they're actually positive. So that's n over 2 times p on average, right? Meaning that we have n over 2 positive samples, and the probability that they're labeled as positive is p, so I can just do this multiplication. And what is the false positive? That means that the ones that are labeled as positive, but they're actually negative, and that will be, again, n over 2 times p, because, again, the chance that you label something as positive is p. And remember, again, because the sum of the probabilities must be 1, this means that the probability you label something as false or negative is 1 minus p. So this gives us the true negatives and false negatives. And now if you do some math here, you can see that the true positive rate and false positive rate, they're equal. And the result is p, which is the probability that we set here, right? So this means that if, for example, the probability that the random classifier assigns positive labels is equal to 0, then true positive rate is 0 and false positive rate is 0, because you never predict anything as positive, right? And then on the other hand, if our random classifier assigns probability p equals 1, meaning that labels everything as positive, then the true positive rate is 1, but also the false positive rate is 1 as well, right? Which is not ideal, right? So that's something that we want to have here, right? We want to have to be sort of like, as I said earlier, this sort of like upper left corner. That's sort of like the example of like a really good classifier. So now let's look at this practice test. So in this case, we have a binary classification, and the labels are +1 and -1. As we mentioned earlier, these labels don't matter what values we assign to them, because the whole idea is that we just need to assign 2 distinct numbers. So either 0 and 1, -1 and 1, or if you want, you can just call them like 10 and 20, right? So any 2 distinct numbers that you want to choose. And here we assume that our data is linearly separable, meaning that we can find a line to separate the 2 classes. And we ask here that which of the following formulation can guarantee to find a linear classifier that achieves 0 training error. So we're looking at the training error here. And we know that, so I can show you this here. So we have this data set, right? So we have one class here, and then we have another class here, and we know that these are linearly separable. So in this case, this is a perfect match for logistic regression, right? Because logistic regression is able to classify this linearly separable data. And the other idea here is that you can see we have linear regression with a square loss. And remember, that one is only used for regression, not for classification. So that's the solution that you shouldn't, or the choice that you shouldn't select here, right? So the logistic regression, and also in future videos, I will talk about support vector machines. So support vector machines is another way of separating linearly separable data sets. And perceptron is here refers to multi-layer perceptrons or neural networks. And those models are also definitely able to classify linearly separable data sets. In fact, logistic regression can be viewed as a simplified form of a multi-layer perceptron. Now let's look at another practice test. So here we have this logistic function that we use in logistic regression, 1 over 1 plus exponential of -t. This is another way of using exponential function. Instead of using e to the -t, we can write it in this form. So the first part is easy. You just want to show that if instead of t, you pass in -t, that would be the form of this function. So that's like a calculus type problem that you can work on. But here what we have in this problem is that let's say you have a logistic regression that you want to use to solve a problem, and we used an optimization problem, and we find those coefficients that we have, right? So remember, we had theta 1, theta 0, theta 1, theta 2, theta 3, because this is a three-dimensional problem, right? So here we have set of features that we have three-dimensional arrays. And also here assumes that we have theta 0 equal to 0. So that's the bias term. And it says that theta 1 is found to be negative log of 4. And then theta 2 is log of 2. Theta 3 is negative log of 3, right? So we solve this problem. We find these coefficients or these parameters. Now, given a new test point, right? So this is a set of features for a test point that all of these features are equal to 1. We want to find the probability that the document is about the sports. And if you look at here, y equals 1 means it's about the sports, y equals 0 means it's not, right? So this is a perfect fit for logistic regression because we have this binary classification problem. Something that is very useful to solve this problem is that exponential and logarithm functions are inverse of each other. It means that if we have exponential of logarithm of any number, let's that call number t, we get back that number because exponential and logarithm, they cancel each other, right? So having all these said, we want to find the probability that if we have a new feature set 1 and 1 and 1, what's the probability that y equals 1 given this feature set that we have? So remember that logistic regression has two parts. The first part is about finding the linear combination, and that's where we have this theta 1 x1, theta 2 x2, theta 3 x3, and all these theta 1, theta 2, theta 3 are given in the previous slide, and we know that x1, x2, and x3, they're all equal to 1. So that's what we get here. And remember two important properties of the logarithm function. Log of a plus log of b is equals to log of a times b, and log of a minus log of b is log of a over b, right? So these are the properties that you have seen in calculus. So given these, we can write this as 2 divided by 4 times 3, because these ones have this negative sign. They go in the denominator. And this gives you log of 1 over 6. Now, in order to find the probability that this document is about sports, so what you need to do is that use the logistic function, which is 1 over 1 plus e to the negative log of 1 over 6. We can use another property of logarithm here, which is log of a raised to the power of b is b log a. So if you have this b here, you can take this to the sort of like the power here. So this means that this negative 1 can go here, right? And now we have exponential and logarithm, and these two cancel each other, which means that we get whatever it's here, which is 1 over 6. And again, one more time, you have to invert this, and that will basically give you 6. So at the end, you get 1 over 1 plus 6, or 1 over 7. So this is the probability that this document with this feature set belongs to class sports. Let's look at another practice test here. So again, let's say here we have these class labels or target labels that are 0 and 1. And again, this doesn't really matter. It can be negative 1 and 1. It doesn't change anything about the hypothesis. In this case, we have two features, x1 and x2. And this is the decision rule that we find using logistic regression. Again, we assume that we have solved the optimization problem, that the class label is 1 if we have this condition, right? And let's say here we have this W1, W2, W0. This is also important to just show you this parameter that we use, they shouldn't just be called theta 0, theta 1, theta 2. They just can be called anything you want. Here we use W0, W1, and W2. And we want to plot this decision boundary and label which regions, means which part of these sort of like feature space that we have leads to us predicting y equals 1 and the other one y equals 0. This is a simple thing because what we are really trying to do here is to plot this line that is given here, right? So we know that W1 is 3, W2 is 5, and then we have the intercept or the bias term, which is negative 15. We can take this to the other side. In order to draw a line, you can always just look at 2 points. X1, 0 means that X2 should be 3, and vice versa, right? So now you can assume that X2 is 0 and X1 should be 5, right? And this gives you this decision boundary. So that's exactly how logistic regression works. You find a line that separates the two classes. And obviously, you can always just check the condition, right? For example, if I put 0 and 0, which is the origin here, we can obviously see that that would be here negative 15, and negative 15 is less than 0. So that's the class y equals 0 on one side. And the other side is class y equals 1. And that's also another way of looking at this. The linear regression aims to find a line that describes the data, means going through the data. Logistic regression finds a line that separates the two classes. So the idea is that you don't want to go through the data, you want to separate the data that we have, the two classes. And then let's look at this another practice test here that asks, when do we expect k and n, which is k nearest neighbor, a very simple classifier that you just look at the k nearest neighbors and you basically use that to figure out what the label of a query point is, can be better than logistic regression, right? So you can see that logistic regression works very well when the data is linearly separable, meaning that you can find a line to separate the data. So you can expect that k-nearest neighbor can do better than logistic regression when the data is not linearly separable, right? Because in that case, right, let's say if we have a data set where we have one class here and then the other class here, right? Obviously, there is no way we can find a line to separate these classes because it's obviously you need something more nonlinear, right? So in that case, k-nearest neighbor can be a much better candidate than logistic regression. So that's why it's very important for specifically machine learning exams to understand the underlying hypothesis or model behind machine learning methods. And the very last question that we have here for this machine learning exam preparation is about, again, logistic regression model. And the idea is that if we add a new feature, so let's say you already have 2 or 3 features for your machine learning problem, and you add a new feature that is set uniformly at random, which means that doesn't have any correlation or any connection with other features that you have. And if you run this logistic regression again on this new data set with the extra feature, what would you expect to happen to the training and testing error of your model, right? So you have the solution here. So you expect that the training loss or the training error to decrease because now we have increased model complexity. Although that new feature may not be correlated with the label or other features, it will allow us to add an additional parameter or coefficient that the learning algorithm can use to fit to the training data that we have, right? So that's why we expect that the training error to decrease. However, you have to be cautious here because this can easily lead to an increase in the testing error because now your learning algorithm will most likely assign a non-zero weight or parameter to that extra or redundant feature, which is kind of like a random noise. And it is very likely that now you may overfit at least slightly to that feature that you have. So you expect that the training error to decrease and the testing error to increase. So that's another way of thinking about overfitting, bias, and variance when you have logistic regression. And as long as you understand the basics, you can see that you can apply them to different machine learning methods. I hope you found this video useful, and see you next time.